Hello, my talk is about bilimits, are bifinal objects, and this is a joint work with Jonathan Arpats and Edoardo Lanari. So let's start from the very basics. Let's just remind what is a limit in the standard categorical setting. Well, we have a functor, f from J to C. J and C are two categories, and the limit of f can be is defined, if you want. One of the equivalent definition is the terminal cone in the category of cones over f. So since we have a two categorical understanding of things, and there is a well-developed two categorical theory, as well as well-developed two categorical limits, etc., all the zoology, one would like to understand if this characterization is still true in the two categorical world. So, is it true that for two categories, and for a two functor f from J to C, two categories, the two limit of f is still characterized by being biterminal in some two category of cones over f? Biterminal is just a property for that if T is an object of C, this is biterminal. If for any other object A, the home category from A to T is isomorphic or equivalent, depending on flavor, to the terminal category. Well, with this definition, Klingman and Moser answered that no, it is not true that we can characterize the canonical notion of two limits with biterminality in the two category of cones over this functor f. But, they added, it is true that some biterminality property characterizes the two limits if we change the two category, so that we don't consider anymore the two category of cones over the two functor f, but we construct some category that they call morphism, the two category of morphism of f, which is constructed essentially by double categorical techniques. Let me just give you a brief reminder on what bilimits are, just so that we are on the same page. So if we have this two functor f from J to C, two categories, and L is an object of C, and lambda is a pseudo-natural transformation from the constant functor on L to F, so that you just imagine this as a cone over F, right? It's just a bunch of triangles with top. The top is L, the bottom is F of some morphism, some one arrow or two arrow of J, and these triangles, like in the classical categorical case, but this time these triangles are filled by invertible two cells. So this pair, L and lambda, is a bilimit of this two functor f if for any other object x in C, it represents some category of cones, right? This bottom category on the right is just the category of pseudo-natural transformation from the constant functor on x to f. So they're just cones starting from x. And these cones starting from x are represented by L, right? It's precisely like in the classical categorical case, just here we have one more degree of freedom given by the two cells. So CXL is a category, not a set, and then this other guy on the right is also a category. There are the pseudo-natural transformation, that are the cones, but there are also modifications of the cones. We can do something very similar, and instead of asking the two cells being invertible inside these triangles that constitute the cones, we can just take any two cell, invertible or not, and we get the definition of lax limit. So it's the same thing, just we replace the invertibility, the requirement of invertibility, we give it up. And this is a lax limit. Of course, one can ask something in between. some triangles to be invertible, some not. This is possible with the notion of marking. This was done, but we will talk about this later. Now, Klingman and Moser answered negatively to the question of can we characterize two limits with biterminality? But what if biterminality is not the right property to look at? What if the right generalization of this property, of this definition of limit, is not the conceptual way to think about to limit, especially because of the biterminality? What if this biterminality is really not the thing we would like to? Well, let's try to play with an example. The archetypical, prototypical example of a category with terminal object is the slice category over an object. And this should be true also in the two categorical case. So C here is a two category, X is an object of C. We have a lax slice, right? So the objects are just one arrow over X, like Y over X, Z over X. And one arrow of this slice is a triangle filled with a two cell, like we draw here. So the identity of X should be some kind of universally terminal object. It must be terminal in some two categorical way. Let's see if it is biterminal. Well, what does it mean? It means that for every f from a y to x, the home category of the slice from f to the identity of x should be isomorphic or equivalent to the terminal category, to the point. But you can easily construct some simple example for which this is not true. Just by some, this home category can be easily seen to be not weakly contractible for some easy example. But if you play a bit more, what you find is that there is a special one arrow in this slice, which is the one arrow filled with the identity for this f. And this object is terminal in the home category, terminal in the classical standard one categorical sense. So it seems that somehow maybe biterminality is not the right property. Maybe what we want is some categorification of terminality. We want some terminality in the home categories, which doesn't mean that the home categories that end with some particular nice object needs to be contractible or equivalent to the point, but they somehow iteratively contain a terminal object, specified terminal object. So how can we test this and make it conceptual? We would like this to be conceptual, not just a made-up definition. Well, we have some different characterization of terminality in the context of one categories, and we can check if generalizing these different characterizations, we end up to the same notion for two categories. So a couple of these alternative characterization of terminality are: X is terminal in C, in the category C, if the embedding of this object X into C is final. Somebody calls this cofinal, but it has to do with the colimits. The second one is that the projection of the slice over X to C as a section, as this section has the particular property of mapping this object X, this terminal object X, to the identity of X. These are very easily checked to be equivalent characterization of X being terminal in C. Let's try to generalize this to a two categorical framework, and let's see if this brings some knowledge, some information about what a definition or characterization of biterminality or alternative notion of biterminality could be for two categories, and if this agrees with this iterated, categorified notion that we've seen for the slice. Well, luckily for the finality of two functors, there is a theory already well developed by Abian Garcia and Stern. It just has a subtlety. It comes equipped with marking. So what is marking here? A marking is simply a bookkeeping device that we put on some one arrows in these two categories to say, okay, this one arrow will have some particular property. There will be some transformation for which, if this arrow is marked, something will be invertible at some point. So this is precisely what happens. If U is a two-factor from B to C, and both B to C are equipped with some marking that here is denoted by EB and EC, then this two-factor U is final. If for any other factor F from C to D, and for any small object X of this category D, we have this equivalence of categories. This definition is precisely equivalent to say that the colimit of F exists if and only if the two colimits, sorry, of F exists if and only if the two colimit of F precomposed by U exist. And if they both exist, they are isomorphic as objects in D. It's precisely equivalent, but it is more useful for us for what we want to do in this context. So what is this equivalence? We have seen these are some category of now cocoons, right? But they have this weird index, EC and EB. So let's look at it a bit more closely. These are just the lax natural transformation from F to the constant factor of X. So they're just cocoons filled by a non-invertible arrow. But this arrow is invertible whenever the top edge of the triangle is the image of some morphism which is marked. So here comes the thing that I was saying. Marking means that at some point with some transformation, this image of the marked one arrow will be invertible at some point. Okay. Let's see what happens with our prototypical example of category with terminal object, which is the slice. So C here is a two category, X is an object of C. And we've seen that the identity of X as an object of the slice should be terminal in a true two-categorical sense. And here we want the characterization with finality with respect to this notion of finality for two factors. Well, if we take the embedding of the identity of X into the slice with the empty marking, this is final. You can actually check that this is final. You can check it with, with this property here, with this definition. But more is true. You can check that the embedding of the identity of X in the slice over X is final, even with this marking. What is this marking? It's a very simple canonical marking. It's simply the marking consisting of the one arrow of the slice, so some triangles having as a bottom tip X, and such that they are filled with an invertible to cell, and one diagonal edge is the identity of X. All right, so this is stronger than the first finality because it's final with a bigger marking. And what does it mean? Well, let's try to go back to this definition. It means that for any two-factor F from C to D, the guy on the left here will do something more than being just a lax natural transformation. It means that for every one arrow in this marking of C, there are gonna be some triangles, some cocoons over X, which are invertible. And this for any factor F and any X in D, right? This marking here. Okay, so it seems to fit a bit in the pattern we want. It seems to be already kind of conceptual. Let's see the other characterization of terminality that we have in one categories and how we generalize to two categories. So the other was a section of the projection of the slice over C. Now, the meaning of this is a bit different, right? We have a category C, we have an object X in C, and we want to say that X is terminal in C, or terminal in some two-categorical sense. So this generalization of this notion of this characterization of terminality for higher categories is known by the name of contractions in the literature. So a section gamma of this projection of the slice over C is a contraction if the image by gamma of X, the wannabe terminal object, is the identity of X, that is precisely like in the one categorical case, and then comes a two-categorical layer. So for each object C, for each object Y, in C, gamma maps this object Y to something in the slice. So a morphism of Y from Y to X. Here is denoted by gamma Y. But we can apply gamma to this one arrow and get a two arrow C. So the other condition says that if you apply gamma twice, essentially, by gamma to a one arrow that is already obtained by gamma, what we get is an identity. This is the two-categorical layer. Of course, we could add some marking. We could think of this gamma X as a marked one arrows of C, and what they do is clear. The action of gamma on this marking gives identities. We can replace all this by a random marking containing the one arrows which are a gamma of an object, and this is just a standard generalization of the notion of contraction. This object X, the wannabe terminal object, is normally called the center of the contraction. What is nice is that if X is the center for two contractions, then these two contractions must be isomorphic. So being a center is a well-defined notion regardless of the contraction we choose, because if there is another contraction, that one must be isomorphic to the first one. So let's try to link this notion of together. Pick a two-category C with a marking containing at least an arrow of the kind Y to X for any Y. See, X is our wannabe terminal object. Then the following conditions are equivalent. The embedding of X into C with this marking M is final. Final in the sense of two colimits, like we said before. There exists an M contraction of this kind, meaning that X is the center of an M contraction, and they are both equivalent to this categorifying notion of terminality that we were talking about in the beginning. So the home category from Y to X is a terminal object. When Y happens to be X itself, the identity is the terminal object, and there is this other condition for which any one arrow which is marked preserves terminal objects in the home categories. So this gives us a conceptual understanding and generalization of the notion of terminality, which is coherent with what we said before. So probably the biterminal object is not the right notion to look at. Instead, we should look at this bifinality notion, if you want to generalize the fact that a two-limit is some two-terminal bifinal object into the cones. And this is what we are heading to. So let me just define two categories of Lax cones. We have functor F from J to C. Here there is a marking E, but you can assume that it's either empty or all the one arrows of J. It just means pseudo or lax. Or better, lax and pseudo. This is a two-functor. What is this two category of lax cones? It's very easy. The objects are the cones over F, so triangles filled with some two cells. These two cells might be invertible or not, depending on this E, this marking E. You can choose pseudo or lax, it doesn't matter much. The one morphisms are some kind of modifications. They are morphism cones, if you want. And the two morphisms are some kind of coherencies between these modifications. This slice, this category of lax cones over F, comes equipped with a canonical morphism, canonical projection to C. And this two-functor, this projection, is some kind of vibration. And since it is a vibration, it makes sense to speak about Cartesian edges, Cartesian one-cells of the vibration. It turns out that one morphism of these two categories of lax cones, so a pair F zeta, of this kind, is Cartesian with respect to this projection, if and only if the zeta I are invertible for any I in the diagram category J. We call this set of one morphism of the one arrows of the two categories lax cones, we denote it by M-cart. This is some marking. It's the marking we need to talk about the right bifinality. What do I mean by this? I mean that this is the marking we need for defining our center to be the limit of this two-functor, right? So with this notion of marking, an M-car contraction gamma with center this lax natural transformation from L to F, this lax cone, if you want, is called limiting. But we said that two contractions with the same center are isomorphic. So we can just say that the cone, the lax cone L lambda over F is called the limiting bifinal, if it is with respect to this marking. Okay? If we have this set, then we can finally confront bilimits and bifinality. In fact, these are equivalent. The pair L lambda is the bilimit of F. F is always this two-functor from J to C. L lambda is limiting bifinal, so it is the center for a contraction with this marking. The marking is very canonical, they are Cartesian cells for canonical projections. And the embedding of this object as an object, as a lax cone, into the category of lax cones is final with respect to two colimits. So we find again the characterization that we had for one categories, and here is kind of categorified, conceptualized for two categories. And essentially what we did is we gave a positive answer to the question we set at the beginning without changing the category of two cones. And we even have more flexibility. We can choose if we want it works both for the pseudo limit and for the lax limit. This is an interesting corollary that was already proved by Klingman and Moser. If this pair L lambda is a bilimit, so it is limited by final, as we said, then if we restrict to the two categories where the one cells are spanned by the Cartesian one arrows, right? The M-cart, what we call M-cart, then this lax cone, L lambda, is biterminal inside this restricted two category. This does not characterize bilimit, but it says that they are biterminal at some point. I think this is all I want to say. I thank you for your attention, and I thank the organizer of Ithaca for giving me the opportunity to talk about this.